There are no secret to success. It is the result of preparation, hard work, and learning from failure. A warm good evening to one and all present here. I, on behalf of the Department of Computer Science, University of Madras, MHRD, RUSA 2.0 Biomaterials team welcomes you all to 2 weeks workshop on analytical tools for image processing, day 12. We all had very useful, interactive, informative, and hands-on sessions for the past 11 days. Today's topic is Stochastic Bio-Models. I request Dr. B. Lavanya ma'am, Principal Investigator, Biomaterials Team 2, to say few words about the resource person, Dr. Uday Bhaskar sir, Senior Professor, Department of Mathematics, Vailtech Rangarajan, Dr. Shakuntala, R&D Institute of Science and Technology, Avadi.
Sir, once again, welcome you, sir. And we are really honored and we are really waiting to listen to your knowledge sharing on stochastic biomodels. It's really an interesting topic, sir, like converting the implementation into model is real challenge for us, sir, actually. So we are really eager to listen to you and honored to listen to you, sir. So may I request Dr. Hannah Vijaykumar, Head Department of Computer Science, Anadesh College, to introduce our resource person to the gathering.
Good evening to all. It is my pleasure to introduce Professor S. Uday Bhaskaran, the eminent resource person, for the 12th day of the 2 weeks workshop on analytical tools for image processing, sponsored by MHRD RUSA 2.0, organized by the Department of Computer Science, University of Madras. Dr. S. Uday Bhaskaran has a rich teaching experience of 50 years, which includes an enormous research experience of 42 years. Sir completed his doctorate in mathematics at Indian Institute of Technology, Madras, and his research work was studies on stochastic integrals and stochastical dynamical systems. His area of specialization is applications of stochastic processes. Dr. S. Uday Bhaskaran is currently serving as a senior professor of mathematics at Vailtech Rangarajan, Dr. Shakuntala, R&D Institute of Science and Technology, Chennai. He has published over 70 research papers in reputed journals. His field of research includes applications of stochastic differential equations, branching processes, and point processes in engineering, biological, and financial problems. Knowledge is power. Knowledge shared is power multiplied. This is a famous quote by Robert Noyce, the co-founder of Intel. I would like to express my heartfelt thanks to the esteemed professors, Dr. Chitra, Dr. Swarnam, and Dr. Lavanya, for this opportunity and for organizing this useful, informative, and enlightening workshop on image processing for researchers and faculty members belonging to the University of Madras. Looking forward to hear from the eminent speaker, Dr. Uday Bhaskaran sir, on stochastic biomodels. Thank you.
Thank you, Dr. Hannah, ma'am. Thank you so much for your kind words. The floor is yours, sir.
Thank you, ma. Thank you, Lavanya. Thank you, Hannah Vijaykumar. I'm very happy to be with you this evening. See, the topic is stochastic biomodels. Stochastic, it's a term which is actually very difficult to pronounce by many people, because as a teacher I came across many times students pronouncing the word stochastic something different. So let us be very clear about the word stochastic. It is nothing but randomness. Anything that is random is called stochastic. It's a synonym. Stochastic, random, they are synonym. So you can call stochastic processes or random processes. Anyway, if anything is random in any model, then it becomes a stochastic model. All of you know that God's creation is humorous.
Excuse me, sir.
Please.
Sir, do you want to share your screen, sir?
Yeah, I have not yet shared.
Okay.
I'm just introducing myself.
Okay.
I'm introducing myself to the audience. The nature is very, 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 very interesting to watch. God's creation is wonderful. Everything you can see different from everything. They say, I am myself. I am different from you. From how many people I am different? So if you take any people, his behavior will be different. We cannot say his behavior is same thing as I behave. So it's a random behavior. It is called a random behavior. So anything that is random is called stochastic. Stochastic involves the probability concepts. If you want to study any phenomena, a random phenomena, you will require knowledge of probability theory. Without the knowledge of probability theory, you cannot, probability concepts, you cannot analyze a stochastic model or random model. Why I have chosen these bio-models? See, biology, you know, the study of creations, living beings, study of living beings, biology. Plant biology, you say, animal biology, you say. When I talk of biological systems, a system consists of several individuals. If I stick on to one particular species, then it becomes a particular biosystem. The behavior of the individuals of the system will be random. The lifetimes are different. The reproductive behavior is different. Everything is different from individual to individual of a system. This difference in behavior requires a model. Unless you put forward a model, we cannot analyze the biosystem. When you make a model for a biosystem, it becomes a biomodel. All of you know that randomness is present in every biosystem. Randomness is present in every biosystem. Therefore, the biomodel now becomes a stochastic biomodel. For study of stochasticity, I told you that you require a knowledge of a little bit of probability concepts you need to know. So I plan to present before you at least 2 biomodels to show the power of modeling a system. I don't say simply by modeling a biosystem, you have achieved quite a lot. You cannot say. The model is only an approximate prototype of a system, in particular biosystem. Model will not depict all characteristics of the system. That point should be very clear to you. When you develop a model, you cannot immediately say that I have studied this biological system. No, cannot say. Then what is the use of the model then? When the model is not able to study completely the biosystem that you are considering in view, what is the point in developing a model? The model is developed in order to predict, at least statistically, the behavior of the system. So this point you should be very clear before you develop a model. I told you already that you require a little bit of probability concepts. Many of you would have studied probability, at least in the school level, 7th standard, probability you would have studied, 12th standard, probability you would have studied. Perhaps some would have studied probability in their degree course also. Probability is an important topic for the study of random phenomena. In fact, if you are more knowledgeable in probability theory, then you will excel in analyzing any system whatsoever with you, in particular biosystems. One of my students who did his BTech course in my university joined for his MS course in Germany. He got a fellowship and he joined there. During the first month, he attended the classes because he was a mechanical engineering student. The first day, the professor who took the mechanical engineering subject told the whole class that I am going to begin with probability theory. This fellow got astonished. That night he called me by 12 o'clock or 1 in the morning. He woke me up. Sir, you are my God. You taught me probability theory, sir. That saved me to attend the class. I think I will do well, sir. I just blessed him. Okay, go ahead. Complete your MS. Continue with PhD, I told him. Now he is doing PhD there. What subject he is doing? He is doing in mechatronics. Really wonderful. So I am able to get some words of gratitude from many of my students who studied probability theory for their higher courses, even for the research. Therefore, my sincere request to all the participants of this workshop to give a sincere attempt to understand the rudiments of probability theory, which I am going to present here, and see how I am going to connect these rudiments to building biomodels. Now I will share the PPT for the day. Are you able to see the screen?
Yes, sir.
So this is a screen I intend to join with you. Stochastic Bio-Models. I am already, they have introduced me to you. And this workshop is on analytical tools for image processing. I felt that I am a misfit to this workshop. Anyway, At the request of the organizers, I accepted and I am with you now. This is the plan of my talk. Today I will complete probability and stochastic processes. And tomorrow's lecture, I will apply these concepts which I developed today, not developing, which I am going to present today, to the study of some stochastic biomodels, in particular to carcinogenesis. What is carcinogenesis? Tumorigenesis, or we can say how cancer is produced, the process of formation of cancer, the process of formation of cancer. It is called carcinogenesis. Right. So this is the plan I have in my mind. Now let me introduce the probability concept. Simple thing. See, there is no need of any advanced mathematics. Start from scratch. Simply you should know addition, multiplication, division. That's all. First, I will tell you what is called a sample space and events. Consider an experiment whose outcome is not predictable with certainty in advance. Although the outcome of the experiment will not be known in advance, let us suppose that the set of all possible outcomes is known. For example, suppose a lady is about to give birth. The girl is about to give a birth. We cannot know in advance. Nowadays, the science is well advanced. They will know what baby is going to she deliver, male or. But in those days, unpredictable. Only after delivery you can soon know that the child is a girl or child is a boy. Let us suppose that the set of all possible outcomes is known, either boy or girl. This set of all possible outcomes of an experiment is known as the sample space. Is known as the sample space of the experiment. And usually we denote the sample space by the capital letter S. Clear? Right. Some examples. If the outcome of an experiment is consists in determination of the sex of a newborn child, then S sample space is equal to G comma B. G stands for girl, B stands for boy. Where the outcome G means child is a girl and B is that it is a boy. Suppose we are interested in determining the amount of dosage that must be given to a patient until that patient reacts positively. Dose response relation. Those who have studied much of statistics, they will recall what is called dose response. Suppose we are interested in determining the amount of dosage that must be given to a patient until that patient reacts positively. What is the sample space for this experiment? So this is the experiment. See, first of all, you should know what is the experiment. Whether the experiment is deterministic or random. Here the experiment is random. Why it is random? Because we don't know what amount of dosage you are going to give. If little dosage is given, the patient may not react immediately. So you have to increase the dosage. So doctor will prescribe, okay, today 5 mg. So wait for 2 days. The patient is not reacting. Therefore, increase the dosage to 10 mg. Like that, the dosage will increase depending upon the reaction of the patient until the patient reacts positively. One possible sample space, See, dosage cannot be infinity, but hypothetically, so this is the drawback in modeling. This is the drawback in modeling. One possible sample space for this experiment is to let the sample space to consist of all positive numbers. All this is a drawback. This is a drawback of the modeling. How you can increase the dose to 10 to infinity? If infinity amount of dose is given, the patient will immediately die. Therefore, hypothetically, the sample space is 0 to infinity, where the outcome would be x if the patient reacts to the dosage value of x, but not to any small dose. So, this dosage, that will be a number in between 0 and infinity. Below x, the patient will not react. Only this is called threshold level. X is called a threshold level. Below x, the patient will not react. When you give x, the patient starts reacting. So he is recovering. So sample space is 0, infinity. 0, infinity means set of all positive numbers. Now here, this sample space is called a discrete sample space. Why discrete? It consists of only a finite number of points, or at most countable number of elements. So this is a discrete sample space, whereas this one is a continuous sample space, because all positive numbers in between 0 and infinity. No, all positive numbers are uncountable. Positive numbers are uncountable. They have no break. In the real line, if you represent the positive numbers, there is no break in the representation. That is why it is called continuous sample space. If you have got any, if you want to communicate to me, you can actually break the, please.
Please stop the background noise that is coming, and your voice is also weak. Please speak louder.
Fine. Wait a minute. Because see, there is actually I am living in a place where there is a workshop adjacent to my house. I have closed all my windows. In spite of that, noise is coming. Anyway, I'll just go and request the workshop people to at least stop their work for a few minutes. Anyway, now I have requested them. They have obliged my request. Right. So you have understood what is a discrete sample space and continuous sample space. Any subset E of the sample space is known as an event. What is an event? It is any subset. For beginners, this will do. Event means subset of the sample space is known as the event. Or you have to say like this. An event is a subset of the sample space. That will be more appropriate. An event is a subset of the sample space. That is, an event consists of possible outcomes of the experiment. If the outcome of the experiment is contained in E, then we say that E has occurred. These things are all available in any textbook. Perhaps if you take up the book by Mehdi, Stochastic Processes by Mehdi, the first chapter is Preliminaries on Probabilities. That you can refer. Mehdi book. M-A-D-H-I. Mehdi, Stochastic Processes. So this is a definition of a event. An event is a subset of the sample space. For any two events, E and F, of a sample space, we define a new event called the union of the events E and F to consist of all outcomes that are either in E or in F or in both E and F. That is E union F. We denote it by U union. The event U union F will occur if either E occurs or F occurs. Likewise, we may also define the new event E intersection F. Sometimes we write, many people write EF. Don't say E into F. Joint, E join F. But for understanding purpose, we'll call it as EF. Sometimes written as E intersection F, called the intersection of E and E to mean the event which consists of all outcomes that are in both E and F. That is the event EF. Event EF will occur only if both E and F occur. So, union of two events concept, intersection of two events concepts. You can use Venn diagram also to represent all these things. I want to make use of the pen. How to get this panel down?
Sir, you could put it in slideshow and see. Sir.
Pardon?
You could put it in the full screen slideshow.
Ah.
Maybe in view you could sit or go below in the taskbar. You see slideshow. The above one where you see the 74%.
Yes.
Below.
Yes.
Yeah, just to that right side. No. Leave that. No. Just come to to the left. Further. No.
Okay, I want to have this this down.
Okay.
This I want to take it up.
So you want to minimize?
I want to hide this.
Yeah, you can use on the top left corner, you can see the cross mark next to one window symbol, then one minus sign on the
Yes,
top. Yeah,
yes.
this will minimize. This will minimize this.
That is right, but I want to take out this zoom panel. Zoom panel.
Oh,
Anyway, zoom panel, I want to get it so that I can make use of the pen.
Okay, while sharing, you would have shared only this screen.
Yes.
You can stop share and then share what you want to share again. On the top of the screen, you can view that stop sharing.
Yes.
And again, you try to share with the window what you want to share.
You mean this, sir?
Yeah. Yeah. Now we are able to see your whiteboard, sir.
Okay. But I cannot use my wacom. I got a wacom with me. I want to use it.
Sir, you are in mute. We are not able to hear you.
Phi represents to the event consisting of no outcomes. If E intersection EF is empty, then we say that E and EF are mutually exclusive. These exclusive events are very important in modeling. Exclusive events are very important in modeling. That is why I have included this point here. If E intersection F is empty, implying that E and F cannot occur together, then we say that E and F are mutually exclusive. Similarly, you say that E and F are exhaustive if U union F is equal to S. That I have not included here. I will include here. E and F are said to be exhaustive if E union F is equal to S. S means sample space, exhaustive. For any event E, we define E complement. I can write E complement as E dash, or I can write it as E raised to the power E, C. I can write this way also. Either E dash or this way. Referred to as the complement of E to consist of all outcomes in the sample space, yes, that are not in E. That is, E dash will occur if and only if E does not occur. Furthermore, if you make the union of E and E dash, it will be sample space. Because what is E dash after all? It consists of all outcomes in the sample space that are not in E. Therefore, you take the union of E and E dash, that will turn out to be yes. That is also an important concept for us for modeling purposes. Right. Now I come to what are called axioms of probability. Before I state the axioms of probability, why this probability comes, that I am going to highlight here. It appears to be an empirical fact that if an experiment is continually repeated under the exact same condition, then for any event E, the proportion of time that the outcome is contained in E approaches some constant value, as the number of repetitions increases. For example, usual experiment. Suppose you toss a coin. Probability, does not stop with this tossing a coin. Tossing a coin helps you to understand the concept. Suppose you consider the experiment of tossing a coin. Coin has got two faces. One face is called head, another face is called tail. So if you toss a coin, the result will be either head or tail. Okay. Now, what is the probability of the event E corresponds to head? What is the chance of getting head in the experiment? It is a random experiment. So for this, you have to repeat the experiment under ideal conditions, exact same conditions for infinite number of times continually. Continually means infinite number of, it is not possible. Even the God sitting at the top of the world, if he tosses a coin, he cannot finish the experiment. Continually repeated under the exact same condition, then what is the probability of getting it? Frequency you have to consider. How many times the head has occurred? Out of so many number of times. That frequency, if you consider, that frequency will approach a certain constant. That limit will approach a certain constant. That constant is called the probability of the event. For any event E, the proportion of time that the outcome is contained in E approaches some constant value as the number of repetitions increases. If it is this constant limiting frequency that we often have in mind when we speak of the probability of an event. So probability of an event is actually a limiting frequency. Fine. So after having understood the meaning of a probability, probability is a limiting frequency. So therefore probability is a number. Probability of an event is a number. Frequency cannot be negative, obviously. Frequency cannot be a negative number. Limiting frequency cannot be a negative number. So probability cannot be a negative number. But limiting frequency can be 0. Therefore, the probability of an event is obviously greater than or equal to 0. That is the first axiom. Probability of E is greater than or equal to 0. Second axiom tells you probability of the sample space is equal to 1. For any sequence of mutually exclusive events, E1, E2, etc., I already told you exclusive events, mutually exclusive events, pairwise disjoint events. EI intersection EJ is empty when I not equal to J. Typing mistake. When I not equal to J, probability of union J equal to 1 to N EJ equal to sigma J equal to 1 to N probability of EJ. Here the N can be 1 to infinity. So the sum can be an infinite sum also. This is a very important axiom. This axiom is applicable only when the events are mutually exclusive. So probability of, suppose you have got two events, E1 and E2. They are mutually exclusive. What is probability of E1 union E2? It is equal to probability of E1 plus probability of E2. Suppose you have got three mutually exclusive events, E1, E2, E3. Probability of E1 union E2 union E3 is equal to P of E1 plus probability of E2 plus P of E3. This P of E3 is the probability of the event E. This axiom, the number it satisfies these three axiom conditions. That number is called the probability of the event. it agrees with the limiting frequency definition of probability. Now, there are certain immediate consequences of the axiom. Probability of E complement is equal to 1 minus E, because E and E complement are disjoint, mutually exclusive. If E occurs, E complement cannot occur. If E complement occurs, E cannot occur. Now, E union E complement is a sample space. Therefore, if you apply the axiom, you are getting P of E plus P of E dash is equal to 1. Hence, P of E dash is equal to 1 minus P of E. Similarly, this addition law can also be derived easily. These two things are needed for me for modeling. Probability of E union F is equal to P of E plus P of F minus P of E intersection F. These two formulas are needed for my modeling. Next, I require conditional probability concept. What is called conditionally probability concept? Suppose I have an event E. I have another event F. They are not mutually exclusive. E and F. So this is E intersection F. I want to find out the probability of E given that F has occurred. Given that F has occurred. What is the probability of E? I am asking you. Given that F has occurred, what is the probability of E? So when you say that F has occurred, you have to look only inside F. Only with regard to F. You need not consider outside F at all. Therefore, probability of E will be proportion of the elements, proportion of the outcomes that are within F, outcomes of E within F, to the number of elements in F. That is called a conditional probability. So what is the proportion? It will be number of elements in E intersection F divided by number of elements in F. That turn out to be simple algebra, probability of E intersection F divided by probability of F. So this is called the conditional probability of E given F has occurred, provided P of F is not equal to 0. Why you say insist that P of not equal to 0? Because it comes with the denominator. If it is infinity, no. If it is 0, what happens? The fraction will become indeterminate. That is why we insist that P of F is greater than 0. P of F is greater than 0. Or not equal to 0. Similarly, what is P of F given E? I know E has occurred. I am asking you to find the probability of F given that E has occurred. See, this slash, some of my students say F by E. You should not say F by E. Several times I want them, don't say P of F by E. Say P of F given E. It is not division. P of F by E. They used to say. We should not say. P of F given E is equal to P of F intersection E divided by P of E. F intersection E is same as E intersection F. So it is same as E intersection F by P of E, provided P of E is not equal to 0. So this is called conditional probability. Why conditional say? Because it is not the absolute probability. You are conditioning on the occurrence of some event. That is why it is called conditional probability. If you cross multiply, you get an important formula which is useful in applications. P of E intersection F is equal to P of E intersection F is equal to, when you multiply P of E into P of E given F into, you can write this way, P of E given F into P of F. Or you can also write P of F given E into P of E. P of. I used to give my student a tip to remember this formula. A tip to remember this formula. When you want to find the probability of simultaneous occurrence of E and F, condition one event, condition any one of the events. Suppose I am conditioning F. I am conditioning F. Probability of E conditioned on F, multiply by the probability of the conditioned event. What is the conditioned event? F is the condition, multiply it. So the same formula would be equal to probability of F given E. F given E. Now I have conditioned E, no? So multiply by probability of E. So this is a very useful formula for our work, for understanding a model, which I am going to present tomorrow. Okay, you have now understood conditional probability. Oh, I have to erase this. I have to clear the board. I have to clear the board. Clear. Clear, all right. Okay. Over. Now let me come to a formula called Bayes formula. For understanding Bayes formula, I start with two events. Suppose E and F are two events. See here what I am going to do with where is that pen? Pen is here. Spotlight pen. Pen is. Sample space can be written as, see the trick here. Why it is not coming? Where is, where is the pen? Pen. Vanishing pen. I don't want vanishing pen. Yes, it is here. Annotate. Yes. Sample space can be written as F union F dash. Very clear. I take now the event E. E can be written as, E is a event. It is a subset of the sample space. Therefore, E can be written as E intersection S. That is very clear. See, S is the sample space. E is a subset. Therefore, you see that E is equal to S intersection E or E intersection S. Take probability on both sides. So P of E is equal to, or substitute for S, substitute for S. So is equal to E intersection. What is S? S is F union F dash. So if you distribute using your knowledge of set theory, is equal to E intersection F union E intersection F dash. Both are mutually exclusive. Therefore, P of E is equal to P of EF plus P of EF dash. This P of EF can be written as P of E given F into P of F, conditioning on F. Here I am going to condition on F dash plus P of E condition on F dash into P of F dash. So which is equal to, you know that P of F dash is 1 minus P. So P of E can be calculated this way. Using this, I can now find using this I can now find P of F given E. I want to find F given E. How to find this? I know P of E given F. I know P of E given F dash, but I want to find P of F given E, which is equal to, by definition of conditional probability, P of E intersection F divided by P of E. P of E. What is P of E? P of E is this. I can substitute, which is equal to the numerator, can be written as I am going to condition upon F. Therefore, it is P of E given F into P of F. See the simple trick. P of E given F into P of F. Into P of F divided by P of E. That P of E is no, this is here. I can substitute here. I can substitute here. What is the speciality of this result? Very wonderful result in the study of probability theory. Lot of applications of this simple result. See, left hand side, you are having the conditional probability of F given E. Right hand side, just you are having the reverse, P of E given F, P of E given F dash. Usually the E will be an a posteriori event. F and F dash, they are a priori events. So given the a posteriori event, you are asking for the probability of the a priori event. That can be got by simply the reverse way. So this gives the concept of a priori and a posteriori probabilities in statistics. So this result, simple result, is called the Bayes formula with regard to two events. This can be extended to any number of events. See here. Suppose F1, F2, etc., Fn are mutually exclusive events and exhaustive events. Exhaustive event means if you take the union of these n events, that will be put in the sample space. Then I can write E, any event E, as a union of these intersections, mutually exclusive. The events are all mutually exclusive. They apply probability on both sides. Probability is an operator here. So P of E is equal to, you can apply the axiom 3 to get sum here, which is now written by using the conditional probability. I am putting Fi in the condition into P of E, Fi. So this I am getting P of E. So from this, you can get probability of Fj. Suppose I want to get probability of Fk, kth event, a priori event, given E. I want to find this. This can be got. How this can be got? Same way, which is equal to probability of E. Probability of E is nothing but here probability of E given F1 into P of F1 plus same way as I did with two events. Probability of P given F2 into P of F2 so on plus dot 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 lastly plus P of E given Fn into P of Fn. So this is a denominator. What about the numerator? They are called a priori probabilities. P of Fn. Numerator will be P of Fk intersection E, which is nothing but P of E given Fk into P of Fk. So this is the Bayes theorem for the Bayes formula in the general setup. But you should know here importantly, F1, F2, etc., Fn are mutually exclusive and exhaustive events. Exhaustive means union will be equal to the entire sample. In other words, random experiment will result in one of these n events. Random experiment will result in one of these n events. That is called exhaustive by saying exhaustive events. That is what you mean by saying that these events are exhaustive. When you say these events are mutually exclusive, if the random experiment results in F1, then F2 will not occur, F3 will not occur, etc. Fn will not occur. If F1 occurs, other events will not occur. If F2 occurs, other event will not occur. If Fi occurs, Fj will not occur if j not equal to I. That is the meaning of mutually exclusive. So these things are very clear for you. Before I go to the next slide, which says that independent events. What are called independent events? If P of E given F is equal to P of E, then you say E and F are independent. If P of E given F is equal to P of E, then you say E and F are independent, not P of F, P of E, which means in words, given the occurrence of F will not influence the occurrence or non-occurrence of E, will not influence the occurrence or non-occurrence of E. Then you say they are independent. P of, I think, madam, I am seeing people are here. P of E given F is equal to P of E, then you say that E and F are independent. Similarly, if you say P of F given E is equal to P of F, P of F given E is equal to P of F, then also you say that E and F are independent. Now you substitute the formula for P of F given E, conditional probability formula, then you can see that E and F are independent, E and F are independent, E and F are independent, if and only if P of P intersection F is equal to P of E into P of F. P of E intersection is equal to P of E intersection F is equal to P of E into P of E. So this can also be used as a definition for independent differential. But I prefer to use only this definition. If P of E given F is equal to P of E, then you say E is independent of F. Okay. Now I come to random variables. What is called a random variable? Random variable is a function which is defined from the sample space to the set of real numbers. In other words, random variables whose set of possible values can be either written as a finite sequence or an infinite sequence. Then it is called a discrete random variable. For example, what are the possible value for a discrete random variable? A random variable with set of possible values is a set of non-negative integers is a discrete random variable. There may exist random variables whose values take on a continuum of possible values. Those random variables are called continuous random variable. I told you in the beginning, random experiment, discrete sample space, continuous sample space. The values of the random variable may be having its value in the continuum. One example of a continuous random variable is this. One example is the random variable denoting the lifetime of a cell when the cell's lifetime is assumed to take on any possible value in the interval 0 to infinity. Infinity is hypothetical. That is why I told you modeling has got some discrepancies also. You cannot have an entity which has got infinite lifetime. All living creatures will have only finite lifetime. But hypothetically, assume that infinite lifetime. When the cell's lifetime is assumed to take on any value in some interval, 0 to infinity. So that random variable is called a continuous random variable. For a discrete random variable, you can introduce what is called a probability mass function. That is definition of this. P of A is equal to probability of X is equal to A. X is a discrete random variable. It takes the value A, probability with some probability, that probability is P of A. So if you change the value A, because X is a random variable, it takes possible values discretely. So if you change the value of X, then the event will also change. In that case, this function will also change. The P of A will be a function of A. This function is called the probability mass function. Similarly, you have got a continuous random variable. Before that, the property of discrete random variable mass function will be summation j equal to P of xi equal to 1. And this is greater than 0. This will be 0 for all other values. So this is a probability mass function definition. Now I have got a continuous random variable. I told you already that the continuous random variable is a random variable which takes values in the continuum. So I'll say the continuum can be minus infinity to minus plus infinity. So the random variable can take negative values also here. Suppose you got a B, an event. X belongs to B is a set of real numbers. the random variable belongs to B, probability of that will be integral over B f of x dx. So Riemann integration, integral over B f of x dx. The function f of x is called the probability density function and satisfies this condition minus infinity plus infinity f of x dx is equal to 1. And if the random variable can take a value between two constants a and b, that probability can be found by applying this formula, integral a to b. Typing mistake, a to b f of x dx. Now I have the definition of a stochastic process. Or before that, I want to introduce something. Probability generative function of x. I think I will close with this. What is the probability generative function of x? Probability generative function. X is a discrete random variable. PGF is defined only for discrete random variable. PGF, probability generative function, is defined only for discrete random variable. So, I suppose x takes the values, say it takes the value from 0, 1, 2, 3, so on, so on. I can label the values of x as 0, 1, 2, 3, etc. So I can now define probability of x is equal to 0. I can define probability of x is equal to 0, which is p of 0, small p of 0. You can write it as p of 0, or you can also denote it as p0. Similarly, in general, you can write Pn. Pn is equal to probability x is equal to n. Probability x is equal to n. So this is the probability mass function. N equal to 0 to infinity. Now multiply the probabilities with some generic variable, say s, some generic variable raised to the power n. Multiply Pn by s power n and sum it over the values of n. N can be from 0 to infinity. This is called the PGF of x. Let me denote the PGF by g of x. It is a function of s. It is a function of s. So for a discrete random variable, you can always associate uniquely a function in this way. That function is called a PGF. Now I will take a discrete random variable. I tell you how to find the. Before that, I will clear this. There is a random variable called geometric random variable. Geometric. Let me take the geometric random variable. What is called a geometric random variable? I explained. I think this I will stop. I think tomorrow I can build up models. Geometric. Geometric means probability that x takes the value n is equal to q power n minus 1 into p, where q is equal to 1 minus p. P is greater than 0. P is greater than 0. And n can be from 1 to infinity, not 0 to infinity, 1 to infinity. So this is called a geometric random. This x is called a geometric random if its probability mass function is in this way. For this, I am going to find the GF, the PGF. How to find it? By definition, it is a sigma n equal to 1 to infinity now, not 0 to infinity, 1 to infinity, Pn. Pn is q power n minus 1 into p into s power n. I can now group this. I can take now p out, one s out. If I take, I will get simply sigma n equal to 1 to infinity q power n minus 1 into s power n minus 1, which is qs to the power n minus 1. N is varying from 1 to infinity, which is nothing but geometric series, which is 1 by 1 minus qs. So this is the PGF of a geometric random variable. I think I'll stop here. Tomorrow I will take up a stochastic bio-model and build up a stochastic model for it using these concepts. Any discussion you want to make here? There is also one random variable, continuous random variable called exponential random variable. Exponential random variable, I told you for a continuous random variable, you need a PDF. If the PDF is like this, lambda into e to the power minus lambda x. The PDF is like this, x is greater than 0. Lambda is a positive constant. Lambda is a positive constant. Then it is called, the random variable is called a exponential random variable. For exponential random variable, we can define what is called the moment density function, mx of t. How it is defined? It is defined as expectation of, I have not defined expectation, e to the power tx. For every random variable, you can define an expectation. Tx is a random variable, e power tx is a random variable. For that, I can define expectation. Actually, expectation of x, or I can take, suppose y is a random variable. Expectation of y is equal to, in the case of a discrete random variable, sigma possible values of y. Suppose the possible values of y are 1, 2, 3, etc. Then I can have probability of y equal to I, that is pi, p suffix I, into yi, into I. So y takes the value I with probability pi. Sum this for all possible values. That is called the expectation of y. Suppose the possible values are from 1 to infinity. So this is called the expectation of y. Like that, we can have expectation of e power tx in this. If it is discrete, then it will be equal to summation j is equal to 1 to or 1 to or 0 to. Anyway, if the possible values from 1 to infinity, then it will be e to the power tj into pj. So this is the definition of a homogeneity function. If x is a random variable, then e of x is called the mean. And e of x square is called the second moment. These two quantities are important for statistical analysis of any biological model. Mean and second moment. In fact, with the mean and second moment, you can get the variance. Variance of x will be equal to, by doing some simple algebra, we can find variance of x is given by E of x square minus E of x the whole square. The variance. These two quantities are interest or of much interest in statistical investigations. Any doubt or any explanation, the additional explanation you need from me?
Professor,
Bro, tell me, sir.
go back to the previous slide.
Sir, good evening, sir.
Please, ma'am.
Good evening, good evening.
This one, sir?
Yeah, no. Your moment generative function definition.
That I have erased. I have erased.
No, you forgot to mention, because it's an exponential random variable, it should be in integration.
Yes, sir. Yes, sir.
Summation for discrete
Oh,
random
yeah.
variable.
Yes, you are right. I'm very sorry. See, actually, you are right, sir. You are right. I'm sorry. I was in a hurry to jump from discrete to continuous.
No, that's okay. That's okay.
Thank you very much for pointing out the mistake, sir. And thank you very much. I'm very sorry. See here, I want to correct myself. As Professor Tangaraj has mentioned, the moment generative function exponential random variable will be mxt will be equal to, because x is a continuous random variable, I must use what is called integration minus infinity to plus infinity. But I told you already, exponential random variable takes positive values only, so it is simply 0 to infinity e power tx into the PDF of x, that is f of x. That is nothing but lambda into e to the power minus dx minus lambda x into dx. Am I right, sir? Is it all right, sir?
Absolutely, sir.
Right. Thank you very much.
No.
Because
I think
because
I was
that is why-
expecting this.
yes,
After your discrete random variable definition for moment generating function.
yes, sir, yes, sir. Yes.
But you skipped it. That's why. That's all.
Maybe that is why, aged people should not be get called for conclave. So thank you, sir. Thank you very much. You are absolutely correct, sir. I'm very much obliged to you, sir. Thank you. Lavanya, please.
Yes, sir. Thank you, Professor Tangaraj, sir, for joining us and honoring us.
Wherever Udaya Bhaskar is there, Tangaraj will be there. Wherever Tangaraj is there, Udaya Bhaskar will be there.
My video is off.
Okay, sir.
No. But it is done by your operator.
Oh, no,
It's
sir.
not allowing.
We don't have such restrictions, sir. Ma Jenny check ma.
I could see Uday Bhaskar now only.
We don't have such restrictions, sir.
No, it is there. Because now when I started,
Okay.
you cannot start your video because the host has stopped it.
Okay. Ma
That is
Jenny
the
check
message
it.
I'm getting it. Now I got it. Start my video.
Good evening, ma'am. Ma'am, I have given access.
I'm able to see. I'm able to see Professor Tangaraj.
Yes, sir.
Yeah.
Background, sir. I think you are sitting on seashore.
No,
Sir,
sir.
Are
I don't want to show my room.
Okay.
It's a virtual background, sir.
It's virtual background.
Very
No,
good.
it is
Very
already
good.
available in the Zoom.
Hmm.
It's not anything new. It is already there. Because my room is, you can see only so many things. It will distract your mind. That is why I put this the virtual background.
But this is
Okay,
attracting.
sir.
This is not distracting, sir. It is attracting me.
Okay, fine. So far, so good.
Tomorrow you are going to see many things.
Tomorrow is an interesting thing. I don't know I'll be able to participate because tomorrow I have online university meeting starting from 3. If it is over by 4, then I will join again.
Yes, sir.
Okay.
Our meeting is from 4 to 5:30, sir.
Yeah. That meeting is at 3 o'clock. I think it don't last for more than half an hour. Anyhow, we'll see. Right?
Okay, sir. Thank you, sir.
See you tomorrow.
Thank you, sir. Thank you so much, sir. Thank you so
you.
much for joining us. Yes, sir. So thank you, Professor Uday Bhaskaran, sir.
Thank you, ma.
Yeah, we'll have a couple of minutes for a vote of thanks, sir.
No, tomorrow also there is one lecture. After that, we can give the vote of thanks.
That will be a detailed one, sir. This is a small today's gratitude, sir.
Okay. Go ahead.
Okay.
When we are thankful for what we have, we are always rewarded with more. I deem it a great honor to propose the vote of thanks to all who have helped us in making this 2 weeks workshop such a resounding success. I thank our resource person, Dr. Uday Bhaskaran sir, Senior Professor, Department of Mathematics, Veltech, Rangarajan, Dr. Shakuntala R&D, Institute of Science and Technology, for your valuable time and for an informative and interactive session. Thank you so much, sir. Thanks for your knowledge. And we are eagerly waiting for the next day session, sir. Let us meet tomorrow at 4 p.m. with Stochastic Models.
Thank you,
Tomorrow's lecture is
Uday Bhaskaran, sir, and thank you, Professor Tangaraj, sir. Thank you. Really, we are really honored to having you with us in our workshop, sir.
Tomorrow lecture is very important as far as your project is concerned.
Yes, sir.
That is why Professor took it as a biomedical model. How it is tackled, how it is coined, how it is tackled, what mathematical techniques you are going to use to justify the title of the workshop, namely analytical tools for image processing.
Yes.
Here the image processing is expressed in terms of carcinogenesis, right? Cancer model. Professor has done a lot of work on this. So I think somewhat it will be helpful for your research work also.
Yes, sir. All these fundamentals as well as tomorrow's portions, actually, it is going to be helpful for all researchers who are working in text as well as in image processing. Sir. The conversion of implementation.
Definitely, you are going to see another racket from Bhaskaran. He will go vertically only. Tomorrow's lecture, because he is going to use integral equations and solutions, finding out solutions, so many things. What he told today, it is only preliminary to the preliminary, right, for his lecture. I hope you can enjoy tomorrow's lecture. That will be a very important one. Okay? Right.
Thank you.
Wish you all the best for the workshop.
Thank you, sir.
Thank you so much, sir. Thank you. Thank you, Uday Bhaskaran, sir. We are waiting for tomorrow's session.
Thank you, ma. Thank you, ma. Thank you.
Yes, sir.
Shall I leave, ma?
Yes, sir. Please. Thank you, participants, for listening to such an interesting and informative session. It's definitely going to be useful. Our tomorrow's session is going to be really useful. For our, actually, that is where any of our computer science professional will be lacking. How are we going to convert our implemented result into a mathematical model? So tomorrow's session is definitely going to be very useful for any type of researcher, whether they are working on image processing